I want you to do something right now. Hold up your right hand. Go on, actually do it. Now, imagine you are standing in front of a mirror. Your reflection holds up its hand too. But here is the question that has genuinely puzzled philosophers and physicists for centuries. Why does the mirror flip your left and right, but not your up and down? Your reflection's head is still at the top, feet still at the bottom, up and down, perfectly preserved, but your right hand becomes your reflection's left hand. Left becomes right, right becomes left. Why does a mirror know the difference between left, right, and up, down? Why does it flip one and not the other? If you just thought, well, obviously it is because, stop. Because I promise you, whatever answer just came to mind is wrong. This question stumped Richard Feynman. It puzzled Immanuel Kant. It has generated serious academic papers in philosophy and physics journals for decades. And today, we are going to answer it properly, completely. And then, just when you think you understand mirrors, we are going to go one level deeper into quantum electrodynamics and show you something about reflection that will genuinely blow your mind. Let us go. G'day, and welcome back to Curious Physics AU, the channel where we take the questions hiding in plain sight, the ones you have walked past every single day, and reveal the extraordinary physics underneath them. I am Abdullah, and today we are tackling mirrors. Not just the left-right flip mystery, though that alone will reshape how you think about space and symmetry. We are going all the way down to the quantum level, to individual photons, to Feynman's revolutionary theory of quantum electrodynamics, QED, and what it reveals about how reflection actually works at the most fundamental level of reality. Because mirrors are not just glass with a shiny coating, they are windows into some of the deepest physics the universe has to offer. Feynman wrote an entire book called QED, specifically to explain the quantum theory of light and matter to a general audience. It is one of my favorite books in all of physics, and mirrors play a central role in it. Today, we are going to walk that same path, from the everyday mystery to the quantum truth underneath. Let us start with the question everybody gets wrong. All right, the mirror question. Why does a mirror reverse left and right, but not up and down? Now, before I give you the answer, let me show you why the obvious answers fail. Obvious answer number one. The mirror flips things because of how our eyes work. Nope. The flip happens regardless of how you look at it. Cover one eye. Use a camera instead of eyes. The flip is still there. Obvious answer number two. The mirror is oriented vertically, so it naturally flips the horizontal axis. This sounds reasonable until you think about it carefully. If you lay a mirror flat on the floor and stand over it, it is now oriented horizontally, but your reflection still has left and right reversed, not front and back. The orientation of the mirror does not explain the flip. Obvious answer number three. Light bouncing off the mirror simply reverses the image, but if that were true, it should reverse both axes equally, up and down and left and right. Why only one? Here's the thing, the mirror does not actually flip left and right. Read that again. The mirror does not flip left and right. What the mirror actually flips is front and back, depth, the axis pointing into and out of the mirror. Your reflection is not left-right reversed. Your reflection is front-back reversed. It is a version of you with your front and back swapped. Your chest becomes your back, your nose points the other way, your front is now facing the mirror instead of facing outward. And here's the key insight. Because humans are bilaterally symmetric, because your left side is roughly a mirror image of your right side, a front-back reversal. Looks like a left-right reversal. Your right hand is on the side of your body that is now facing left in the reflection. Not because the mirror flipped left and right, but because your entire depth axis was reversed and your body happens to be symmetric. Front to back is not the same as left to right. The mirror is not confused about left and right. We are confused about what the mirror is actually doing. The mirror flips depth. Our brain interprets that depth flip as a left-right flip. Because we are standing upright and our up-down axis is not symmetric in the same way, the depth flip does not look like an up-down flip. It looks like a left-right flip. The mirror is innocent. Our intuition is the problem. Now, that explanation is satisfying at one level, but Feynman would push further. Because the left-right question connects to one of the most profound concepts in all of modern physics, chirality and symmetry. In physics, we distinguish between things that are symmetric and things that have handedness. A sphere is perfectly symmetric. Rotate it any way you like, it looks the same. But a helix, like a spiral staircase, has handedness. A right-handed helix and a left-handed helix are mirror images of each other, and crucially, they are not the same object. You cannot rotate one to make it look like the other. This handedness, called chirality in physics, turns up everywhere. DNA is a right-handed helix, almost universally across all life on Earth. Many molecules come in left-handed and right-handed versions, called enantiomers. The left-handed version of the amino acid alanine is found in living things. The right-handed version, almost never. And in particle physics, something astonishing was discovered in 1956 by Chinese-American physicist Chen Xiong Wu, building on theoretical work by Li and Yang. The weak nuclear force, one of the four fundamental forces, actually treats left and right differently. It violates what physicists call parity symmetry. The weak force has a preference for handedness. The universe itself is not perfectly left-right symmetric. So when you look in a mirror and notice the left-right flip, you are brushing up against one of the deepest asymmetries in nature. The universe has a preferred handedness, and mirrors, by reversing chirality, create a world that is physically distinct from ours at the level of fundamental particle physics. A mirror image of our universe would have DNA winding the other way, life built from the other amino acids, a weak force that behaves differently. Your bathroom mirror is a portal to a universe that cannot actually exist as we know it. Right. Let us talk about how reflection actually works. Starting with what your school textbook told you, the law of reflection. The angle of incidence equals the angle of reflection. Light hits a mirror at a certain angle and bounces off at the same angle on the other side of the normal. Your HSC and VCE textbooks have diagrams of this. Neat little arrows showing light bouncing off a flat mirror surface. Clean, simple, satisfying. And for most practical purposes, designing optical instruments, building telescopes, understanding how your rearview mirror works, this description is perfectly adequate. But it explains nothing about why. Why does light bounce? What is actually happening at the surface of the mirror? Why does the angle of reflection exactly equal the angle of incidence? Not approximately, not roughly, exactly. The classical explanation is that the electromagnetic wave of incoming light drives electrons in the mirror surface to oscillate. Those oscillating electrons re-emit light, and the geometry of the re-emission produces the reflected beam at the correct angle. That is a better explanation than just drawing arrows, but it still feels incomplete because it describes what happens, but not the fundamental mechanism underneath. For that, we need Richard Feynman, and we need quantum electrodynamics. And I want to warn you, the quantum explanation of reflection is deeply strange. It challenges every intuition you have about how light behaves, but it is the most accurate description of physical reality that science has ever produced. Buckle up. Quantum electrodynamics, QED, is the quantum theory of how light and matter interact. It was developed in the late 1940s by Feynman, Julian Schwinger, and Shinichiro Tominaga. It is the most precisely tested theory in all of science. Its predictions match experimental measurements to more than 10 decimal places, and it describes reflection in a way that is completely unlike anything your school textbook suggested. In QED, a photon traveling from a light source to your eye after reflecting off a mirror does not take a single definite path. It does not simply bounce off the mirror surface at the point of equal angles. Instead, the photon takes all possible paths simultaneously, every possible path from the light source to every possible point on the mirror surface, and then to your eye, all of them at the same time. Each path has what Feynman called a probability amplitude, a kind of rotating arrow. He called it a little arrow or a stopwatch that represents the probability of the photon taking that particular path. For most paths, the arrows of neighboring paths point in wildly different directions and cancel each other out. The probabilities cancel. But for one special region of the mirror, the region near the point of equal angles, the arrows from neighboring paths line up. They point in roughly the same direction. They add up, they reinforce each other. And it is precisely that region, where the quantum probability amplitudes add up, that corresponds to the classical law of reflection. Think about it this way. Imagine you are at the MCG, Melbourne Cricket Ground, and you want to get from the southern stand to the northern stand as fast as possible. There are 1,000 different paths you could take. Most of them are longer and slower. They cancel out as bad options. But there is a region of paths through the center of the ground that are all roughly the same length. The fastest options. Those paths add up. They reinforce each other, and the average of those similar fast paths gives you the optimal route. That is precisely how QED works for light. The paths near the classical reflection point all have similar journey times, similar phase, and they add up to give you the reflected beam. The law of reflection, the angle of incidence equals angle of reflection, is not a fundamental law imposed on light from above. It emerges from the quantum behavior of photons exploring all possible paths simultaneously. The simple arrow in your textbook diagram is the classical average of an infinite quantum calculation. That is the real physics of your mirror. Now, here is where QED and mirrors get genuinely mind-bending. In the classical picture, only the central part of the mirror contributes to reflection. The edges of the mirror are irrelevant. Light bounces from the middle. Simple. But in QED, all parts of the mirror contribute, including the edges, including the parts where the classical law would say no reflection possible from here. Normally, the contributions from the edges cancel out. The probability amplitudes from edge paths point in all different directions and sum to nearly zero. But, and this is extraordinary, if you scratch or cover the mirror in a very specific pattern, removing the parts that cancel, you can make the edge contributions add up instead of cancel. When you do this, you create what is called a diffraction grating. A diffraction grating reflects light from regions of the mirror that classical optics says should be dark. It can make red light reflect at one angle and blue light at another angle from the same surface. Every rainbow you have ever seen on a CD or DVD, that is a diffraction grating. Those circular tracks on the disc are the precise pattern needed to make certain path contributions add up for certain colors of light. The colors on a CD are not paint, they are not dye, they are pure quantum mechanics. The interference of probability amplitudes for photons taking different paths across the disc surface. Next time you pick up a CD at a garage sale, you are holding a quantum mechanics demonstration. And here is the beautiful connection. The diffraction grating only makes sense through QED. Classical optics cannot explain why a scratched mirror suddenly reflects light from new directions. Quantum mechanics, Feynman's path integral approach, explains it perfectly and precisely. Your mirror, your CD, your understanding of light, all of it, quantum mechanics. Let us talk about a different kind of mirror, one that most people never think of as a mirror at all. Total internal reflection. When light travels from a denser medium, like glass or water, to a less dense medium, like air, it bends away from the normal. This is refraction. Your HSC and VCE syllabus covers this. But here is the bit that is extraordinary. If the angle of the light hitting that glass-air boundary is steep enough, beyond a critical angle, the light does not pass through at all. It reflects perfectly. 100% of the light bounces back inside the glass. No mirror coating needed. Just geometry and the physics of light crossing a boundary between media. This is why optical fibers work. Those glass fibers carrying internet data under the Pacific Ocean from Australia to the rest of the world keep the light inside using total internal reflection. The light bounces along the inside of the fiber, reflecting perfectly off the glass-air boundary thousands of times per meter, traveling from Sydney to Los Angeles without ever escaping the fiber. Your Netflix stream, your video calls, your entire internet experience depends on total internal reflection. On light bouncing off a boundary it cannot cross. And here is the QED connection. Total internal reflection, like ordinary reflection, can be understood through Feynman's path integrals. The paths that would normally transmit through the boundary now have amplitudes that cancel completely in the transmitted direction and add up entirely in the reflected direction. The boundary becomes a perfect quantum mirror. Physics is everywhere, including in every YouTube video you have ever watched. Now let us zoom out, way out, because mirrors do not just sit on your bathroom wall. They sit at the heart of our understanding of the cosmos. Every major optical telescope on Earth uses mirrors, not lenses, to collect and focus light from distant stars and galaxies. The reason is beautifully simple. Lenses refract light. They bend it as it passes through. But lenses have to be perfect all the way through their volume. Even tiny imperfections in the glass ruin the image. Mirrors only need to have a perfect surface. The light does not pass through, it reflects off. So a mirror can be made far larger and far more precisely than any lens. The James Webb Space Telescope, launched in December 2021, has a primary mirror 6.5 meters across, made of 18 hexagonal gold-coated beryllium segments, folded up to fit inside the rocket, unfolded in space. It is so sensitive it could detect the heat of a bumblebee on the moon. And every image it sends back, every picture of galaxies formed just after the Big Bang, every glimpse of exoplanet atmospheres, every extraordinary revelation about the early universe, begins with photons reflecting off that golden mirror surface. QED, Feynman's theory, running in the vacuum of deep space, governing the reflection of photons that have been traveling for 13 billion years. And there is one more mirror in the universe that dwarfs all of these. General relativity, Einstein's theory of curved spacetime, predicts that gravity can bend light. Massive objects like galaxy clusters act as gravitational lenses, bending and focusing light from objects behind them. In some configurations, gravity creates multiple images of the same object, arcs of light, rings. Repeated reflections caused not by glass or metal, but by the curvature of spacetime itself. The universe uses gravity as a mirror, and we read those mirrors to understand the structure and history of everything. I want to close with something Feynman said that has always stayed with me. He said, "I think it is much more interesting to live not knowing than to have answers that might be wrong." That principle is at the heart of everything we have covered today. A mirror looks simple. You have used one every day of your life. And yet, underneath that apparent simplicity are layers of physical reality that took humanity centuries to uncover, and that still contain open questions today. Why does the universe have a preferred handedness at the level of the weak force? We know it does, but we do not fully understand why. Why does QED work so extraordinarily precisely? What deeper theory underlies it? We do not fully know. How exactly does consciousness arise from the quantum and classical physics of neural systems, such that you can look in a mirror and recognize yourself? That question is genuinely open. Every time you look in a mirror, you are seeing the output of quantum electrodynamics, photons exploring every possible path, probability amplitudes interfering. The most precise physical theory ever constructed, running in real time, on the glass above your bathroom sink. You are looking at quantum mechanics every morning before breakfast. Feynman would have loved that. He would have said, "You do not need to go to a laboratory to find the extraordinary. The extraordinary is already in your bathroom. You just need to look at it with curious eyes." So let us bring it all together, Feynman style. Mirrors do not flip left and right. They flip front and back. Depth. Our bilaterally symmetric bodies make that depth flip look like a left-right flip. The mirror is innocent. Our intuition is the problem. The left-right flip connects to chirality, handedness in physics, and to the fact that the universe itself violates left-right symmetry at the level of the weak nuclear force. Classical reflection, angle of incidence equals angle of reflection, is the average outcome of photons simultaneously exploring every possible path described by Feynman's quantum electrodynamics. Diffraction gratings, like CDs and DVDs, manipulate those quantum path contributions to produce spectacular color effects from a surface that classical optics cannot explain. Total internal reflection keeps light inside optical fibers, carrying Australia's internet across the ocean floor. And the universe uses gravity itself as a mirror, bending light around massive objects to reveal the structure and history of the cosmos. If this video made you see your mirror differently, genuinely differently, smash that subscribe button and join the Curious Physics AU family. This is exactly the kind of physics I love sharing every week. Drop a comment below. What surprised you most? The left-right flip explanation? The QED path integrals? The CD as a quantum experiment? Tell me what rewired your thinking. Share this with a mate who loves physics, or one who looks in the mirror every morning and has never once wondered what is actually happening. Now they will. I will catch you in the next one.